Okay, so in that last video, I think it cut off right as we were doing example 2. So again, we're going to find the limit as x approaches 3. We're using the same parabola, but we're doing the table now. We should get the same answer as we did when we found the limit on the graph and when we found the limit with direct substitution. When I go to my calculator, I have my y equals with that equation in it. And remember for my table setup that I am on this ask feature, which means that initially in my table, there's no x values until I start to type them in. So since we are looking for the limit as x approaches 3, we use some numbers smaller than 3, like 2.9, 2.99, 2.999. They're getting closer and closer to 3. We try 3 to see if the limit does exist and if it's actually going to be reached. And then we get a little bit bigger than 3, and then a little bit bigger, and then a little bit bigger. So you have numbers coming from the left, smaller numbers, and numbers coming from the right, bigger numbers. And we see that as the x values come in and approach 3, the y values are approaching 6. So you could write this in your table. I'm not going to take the time to copy it into my table, but you could fill those values out in your table and see that as the x values approach 3 from the left or from the right, the y values approach 6. They're getting closer and closer to 6. This is the same that we got when we looked at the graph and when we did direct substitution. Because direct substitution worked, that means that yes, our limit is possible and it is reached. So our limit is 6 and f of 3 is possible. In our table, we got 6. Our function is continuous at 3. I am not going to walk through number 3. You are welcome to try that on your own. And you can check your answers by thinking about what we said for the limit as x approaches 0 when we did direct substitution and when we looked at the graph. We are going to continue on with some more limits that are actually the ones that are more common or more interesting. Those first couple examples we used for basics, but they're kind of boring because they are continuous. Most of the time, we're going to talk about when things are not continuous. We did some functions like this, these rational functions back in chapter 2, and we are going to look at these next where there's a hole. So for example, we have a hole here at x equals -1, or a vertical asymptote here at x equals 3. When we think about the domain of our graph, last year in Algebra 2, you probably would have said all real numbers except x does not equal -1 or 3. This year in pre-calc, we used interval notation. So we said, well, our graph is valid from -infinity to -1. We used parentheses to say that that interval does not include -1. Then our graph is valid again from -1 to 3, and then finally 3 to infinity. Since we're talking domain, we're using x values. You can see that we have this gap here at -1, that's our hole, and we have this gap here at 3, that's our asymptote. So in those gaps, our domain does not exist, our function is not valid. So our hole is at x equals -1, and our asymptote is x equals 3. These are the interesting points. So in a minute, when we look at limits, we're going to look at the limits for these values. At both -1 and -3, our function does not exist. There is a gap or a hole. It's not in our domain. Our function is not continuous. Because it's not continuous, we cannot use direct substitution. So as we move forward with these next couple examples, we can't do direct substitution. So we must use the graph or the table. So first we're going to look at the hole and talk about how you find limits at a hole. Okay, so for this one we are looking at, oops, sorry guys, hold on. For this one we are looking at a hole. Oh my gosh, my stylus just died. Hold on guys. Okay. So x is approaching -1. So we are looking at our graph as x approaches -1. And remember, we are thinking as x gets close to -1. It doesn't actually get there. We already talked about there's a hole there. But as x gets close to -1, so I come from the left and I come from the right, numbers that are littler and numbers that are bigger, it looks like maybe we're approaching, let's say like 0.8. 0.9, you're kind of estimating there since it's not exact. Okay. but that's the y value. Remember, this answer is always going to be a y value. Okay, so at a whole, you do have a limit. The left side and the right side do approach the same thing. So now let's look at the asymptote. So our asymptote is at x equals 3. This one is different. So here's what I want you to do. If we think about, sorry about that. If we think about this graph, if I am coming at this asymptote here, here's our asymptote in purple. I'm going to change colors. If we think about coming from the left, we're going down to negative infinity. If we come from the right, we are going up to positive infinity. If you trace this with your fingers, you're going down on one side and you are going up on the other side. So your fingers are going different directions. So your left and right side do not go the same direction. So one of our issues here is that our function does not exist if left and right differs. And in this case, that's what's happening. You also know that when you approach infinity or negative infinity, your limit does not exist. So our limit does not exist for two reasons. We're going to say the limit does not exist. And you either could say because the left-hand side and the right-hand side differ, or you could say that your left-hand side approaches negative infinity, or it decreases without bound. It cannot decrease without bound, while your right-hand side approaches positive infinity. So they are increasing or decreasing without bound, which is another valid reason for saying our limit does not exist. So as you look at this next part, this summary, this part is super, super important, okay? So I would just maybe like highlight this or circle it or make it bold or something. Does a limit exist at a whole? Yes, you can find a limit at a whole. Does a limit exist at a vertical asymptote? No, because at an asymptote, you're going to infinity. Okay, so we're going to look at this new function and try that same idea with a different problem. So this is only the second problem in the whole packet. So far, we've been using that parabola the whole time, and then we just went to this rational function. So here's another rational function. And here's what I want to remind you. If you have a factor on top and bottom, remember that factor is going to be a whole. So we are going to have a whole at x equals -1. So already when I tell you x is approaching -1, you are going to know that we do have a limit. We do need to find this, okay? So it says fill in the table. So I'm going to go to my graphic calculator here, and we're going to get ourselves set up. First of all, I want these other values that are in there to disappear. So I'm just going to delete those out so that I don't have unnecessary information in there. Then I need to realize that I have a new equation. So I need to get rid of my original equation. So I'm going to do that alpha y equals to get our numerator denominator. On the top, my function says x, hold on, it doesn't like that. So on the top, my function says x plus 1 as one factor, and then my other factor is x minus 2. And then in my denominator, as I click down there, one of my factors is again x plus 1. And my other factor on the bottom is x minus 3. So here is our function. We can look at the graph, and I hope you think that graph looks familiar. If you look at the graph at the top of the worksheet, remember you can't see holes, okay? If in your table setup it was still on this auto, then when you go to your table, you would see at -1 there's an error. So even though we can't tell in the graph that there's a hole, you can't see that here, I can see in the table that things are problematic at -1 and problematic at 3. 3 is obviously the asymptote, so that's maybe a little easier. But we want to find the limit. Since we know there's a hole, we're now going to find the limit. So we're going to go to this ask feature so that we can put in the table values that we would like. So now my table is blank, there's nothing in there, and I'm going to type in what the worksheet says. We have -1 0.01. We have negative 1.001. Oh, I just lost my table. Sorry about that, guys. Hold on one sec. Okay, negative, nope. Negative 1.01, negative 1.001, and negative 1.0001. So we're farther to the left, we're more negative, and we're getting closer and closer to negative 1. Notice that my calculator just rounded right there. I don't know if you saw that happen. If I get rid of that, I'm going to type this in again, negative 1.0001. So do you see this is what I typed? Now watch very carefully. When I hit enter, it rounds that because your calculator only rounds to 3 decimals. If I actually type in negative 1 in my table, it's going to say error. So remember, in this situation, we were rounding. And in this situation, we are actually typing in negative 1. Now we get a little bit bigger than that. So now we have negative 0.9999. Again, it rounded that. Negative 0.999 and negative 0.99. So you can fill those out in your table. I'm just going to look at these and see what's going on here. I don't actually love that these are fractions. You can change that in your mode. So if you want to say that I would like to change these to decimals, let's see, I could do this, I think. I'm going to tell it to do like 4 decimals. And then if I go back to my table setup, it should round those for me. Nope. So you are going to probably want decimals. I think that's an easier way to see. Here we go. We want our answers in decimals right there. That's what I just changed, answers to decimals. And I can turn this back to float, so that's not bothering us. So now in my table, it gave me decimals. With the decimals, I think it's more clear to see what are my y values getting close to. 0.7501, 0.75, error, 0.75, 0.7499, 0.74994. You can see those are definitely approaching 0.75. So I would say my limit is 0.75. That's what these are approaching. So as I go back over here, my limit is 0.75. We filled out the table in our calculator. That is the limit as x approaches negative 1. And no, the limit does not get reached. Our function is not possible at f equals negative 1. So because our function is not possible at f equals negative 1, our function was not continuous at f equals negative 1, then we don't actually reach the limit. We do have a limit, but we don't actually get there. We're going to do the same thing for our asymptote. Our asymptote was at f equals 3. So now we're going to fill in this table for 3 to see if we have a limit here. So my function is still the same. I don't need to change my y equals. I am going to go back to my table, and you can either type on top of these or you can delete them, whatever you prefer. So now my table says, well, what if we have 2.9 or 2.99 or 2.999? So I'm getting closer and closer to 3. At 3, it's undefined. That's your asymptote. What if we get a little bigger than 3 or a little bit bigger than 3 or even bigger than 3? So you can see our x values are approaching 3. Our y values either go super negative or super positive. You can see these get bigger, bigger, bigger. These get more and more negative. So you're going down to negative infinity here, going up to positive infinity here. So on your screen, I would say here that your limit does not exist. Hold on, I lost my stylus. Give me 1 second here. Does not exist. Sorry. Your limit does not exist. One side was going down to negative infinity, the other side was going up to positive infinity. So our left and right sides differ. Or you could say one side increases without bound and the other decreases without bound. So we're dealing with that infinity issue. So this should get you basically through your homework for 11.1. Make sure you remember those 3 ideas of why a limit does not exist. You should be able to find a limit from a table. You should be able to find a limit from a